So today, basically, we need to finish up part 9, go back, pick up part 3. So I think I probably mentioned that before. Part 9 on titrations, and then part 3 on burning stuff. Okay. So in order to do this last titrations problem, we need to talk about this thing called, this thing that ionic compounds do in solution. And we've talked about it before. They break up into to cations and anions. Ionic compounds basically are cations and anions paired up in that crystalline lattice structure. We'll talk more about that. But basically when they dissolve, they form little ions that run around and conduct electricity. So you guys did a homework where basically you looked at salts, these are salts, and you looked at dissolving them in water and what you got once you dissolved them in water. Okay, and then you guys did a problem like this, where basically if this is 0.230 molar, when it ionizes or dissolves in water, you get 2 parts of the NO3 minus. So the molarity of the NO3 minus is 2 times 0.230 or 0.460, but you have to do factor label. Okay, so I think this is a problem that you just handed in. Okay, so now spectator ions are kind of like spectators in the stands. Okay, spectator ions, like this says, they don't really play a role, they just kind of float around. So honestly, in a minute, when we come up with another form of equation representing the reaction, we're going to say those spectators, they don't do anything anyway, and we are going to remove them from the net ionic equation. Why? Because they don't do anything. Okay. So now, as I was going over this in my office, I'm not going to ask you to write a net ionic equation right now, but I'm going to give you a reduced equation and kind of try to show you the spectator ions that were removed. How's that? And we're going to do another titration problem. So, spectator ion. Spectator ion is just there for the ride. So if it's just there for the ride, it's there in the reactants and it's also there in the products. And kind of like this alludes to, you recognize if it's in the same form on the reactant side as on the product side, they cancel each other out. If it's in the same form, it's in the same amounts. Okay, busy problem, right? But you guys are going to work this, okay? So if you read it a few times, I'm just going to kind of give you the condensed version or point out a few things. All of those words up there, there's several reactants that are given. And honestly, this paragraph, as I was reading it over in my office, it doesn't tell you what's formed. It just gives you the reactants. So it says that you have reactants, the oxalic acid, sulfuric acid is another reactant. I'm going to change my color. And the thing that you have in the burette is potassium permanganate. Okay, so 1, 2, 3. Oops, 3. Okay, 3 reactants, and they don't tell you what the products are here. I'm going to give you the equation here in a minute. I wouldn't ask you to pull the equation out of this. It goes on to give you some information about what was in the burette, what was the titrant. It goes ahead and it tells you the volume, okay, and it wants to know the molarity. It also gives you the mass of one of the reactants. The third reactant, the sulfuric acid, do you kind of see approximately 100 milliliters of one of the 3 reactants? You're like, dude, this is slosh. I'll put the word slosh. I don't know if that makes sense to you. But there's sufficient, it's in excess. Okay. So that's kind of the situation for this particular chemistry. Now I'm just, as it relates to doing a solution concentration stoichiometry problem. So the stuff in the burette, the potassium permanganate, okay, actually that's aqueous, so it's floating around as K pluses and MnO4 minuses. The sulfuric acid that we have in excess, okay, it's floating around as H pluses and hydrogen sulfates, HSO4 minuses. So do you see where the arrow is over here? The way this works is we care about this and we care about this. We don't care about these. Bottom line. I'm just kind of walking you through the concept, in a sense, of removing spectator ions and writing a net ionic equation. So with that in mind, and I haven't told you what the products are yet, finally now I'm telling you the products. So do you see where I didn't care about the potassium, I just want the MnO4 that's in the burette. I didn't care about the HSO4 minus, I just wanted the hydrogen ion that the sulfuric acid gives. And here finally is the first time that you see the products. I'll just put P for products. Okay. Now this is what I would give you. Okay, but I just wanted to kind of talk you through that this is the chemistry that's going on. Remember that actually the mass, a specific mass, and I'd have to look back in my notes, you have it handy. The mass of this was given, right? And the volume of this was given, and you're supposed to find the molarity of that. You guys did some problems kind of like this that you handed in today. If you have the mass of something like that, the oxalic acid, one of the first things we're going to do, or you guys are going to do, we're going to use the mass to get the moles of the mass and the molar mass of H2C2O4 to get the moles of H2C2O4. Okay? And, you know, if you've done many of these, if you've had the opportunity to do many of these, you know then we're going to go from moles of the H2C2O4 to moles of the MnO4 minus. Not too bad, using a stoichiometric ratio, kind of a 2 to 5 sort of thing. That's exciting. Okay, and then once you have moles of the MnO4 minus, you're back to kind of what you guys were doing problems that you're handing in today too. Once you have the moles, you were given the volume, so we can knock out the molarity. So basically we're going to take the answer to 2, which is the moles, and we're going to divide by the volume, which was given, to get the molarity. That's kind of in a nutshell what you're going to do. So as we pass this around, okay, that's kind of our strategy. That's a net ionic equation. Okay. So, let's see. I think this is the slide where it's a cleaner slide where I'm just going to kind of emphasize again. We have the mass of the H2C2O4. So I would usually, underneath that, write 0.2585 grams. Okay. The other information, quantity information that was given was the volume of the MnO4 in the burette, 22.35 milliliters of KMnO4. And then the H plus is in excess. Remember, the H plus comes from our H2SO4. Alrighty. And do you guys have the molar mass of these things? Okay, so that'll be the first thing that we'll do. So, molar mass to you, and then you're going to take her, let's see, how do we do that? Yeah, molar mass to you, and then you're going to use the mass, that mass, and her molar mass to knock out moles.
So, I need the molar mass
of the KM. Oh, wait a minute.
Yeah.
Yeah. Yep, you're going to get the molar mass of, not that, you're going to do the molar mass of the H2C2O4. Yep. So she's, in order to get to moles of this, we're going to first go the moles of this from its mass, from the molar mass of H2C2. I know I'll let you tap that in your calculator. I keep changing up, like, you use a calculator, you pass it on. So you're gonna get the moles, and then Matthew, you're gonna use the moles that Heather gets, and the moles of the H2C2O4 that Heather gets, and you're gonna go to moles of MnO4 minus using up. And then that leaves you with molarity. He's gonna give you the moles of MnO4 minus. Yay. That looks familiar. Thank you. Heather. I think this eraser would work on an iPad. No, I don't think so. Oh, I don't know. That's awesome. Yeah. I finally found a stylus I like. It's like got like wire mesh on it instead of the kind of the rubbery. It's called a True Bone. Yeah, that's right. This is one I thought I lost. My husband hasn't taken his out of the package, so I am so eyeballing that one. I bought them both. So, dude, if you want it, you better take it. So she's going to use the given mass of the oxalic acid. Molar mass to moles. She's going to give us 3 sig figs. 4 sig figs. Very good. 4 sig figs because that's what it has. Very good. And that's moles of H2C2O4. Very good. We're going to go to hopefully another page. So you got that? How about doing it up here? Do you have enough room up there, Matthew?
Yeah, I should.
So he's going to kind of do it. Very good, yeah. I'm going to show you a trick. So if you ever want to like make it bigger, you take 2 fingers and put it on there and it makes it bigger. Is that not cool or what? So, and then if you want to move it over, you just got to use 2 fingers again.
All right. Let's see.
Very good. He's using the coefficients.
Yeah.
This and very good.
I'm looking for MnO4.
Yep. And then a 4 minus. Perfect. Any questions? Can you go ahead and divide that out, Matthew, and we'll pass it back to Jason. So 2/5 of that.
2.
Very good. He's getting ready to catch the ball. Football season. Perfect. Any questions? Awesome. All right. Then we're ready to knock out the molarity. Oops. Dun, dun, dun. It always looks so easy in class. And like I would agree with Jason, if you, with that blue label up there, you don't really have to be explicit with regard to moles or volume of what. we've kind of gone to, whoever does it, then knocks it in their calculator. Well, how would you use it? 4 sig figs? Very good. The one thing I guess I would say, and this is because it's a little bit related to the spectator ion, is this problem I would have rather done, I said it, you don't need to be explicit, but 1148, and that was the moles of the ion. Okay. What you might, the volume, what you might want to have done is recognize, I would have counted this right, by the way, is recognize that the solution is the K MnO4. And then you could have inserted one relationship that for every 1 mole of KMnO4, there is 1 mole of MnO4 minus. Okay? Just basically kind of inserted that right there. And then, of course, your last term still would have had to have been up there. 1 milliliter over 1 liter. I would have been fine, though, with the other. All right. Good job. So then these 2 problems that are due, 63 and 64, we're going to take a look at those before you leave. Okay. Oh, let's take a look at them now. So these will be, I didn't add anything to them, so just bear with me. 63, 64. Where's my 63? Direct. I'm going to go out and find it. Screenshot. There it is. Okay. So, I know this looks like a lot of stuff, like what the heck? But I'm telling you, you take that paragraph and you lift out from that paragraph and put it under the thing it's talking about, and then see what you got, okay? So it says again, it's a KMnO4. Probably the K is a spectator ion. Okay, is used to standardize against a solid. See that As2O3? That's a solid. It gives you the mass of the solid. Let me go ahead and write that under there. Okay, whoops. Oh, really? Come back. So I'm going to write the mass of the solid under there. Thanks. Really? I keep hitting that wrong. I should just, one more time. It's only doing what I'm telling it to do. Okay, I'm already in pen mode. Don't hit the little pen button or it'll go away. So we're going to put this little mass under the 5 moles of it, 0.1078 grams. Okay, and then that volume actually we're going to put under the MnO4 minus. Okay, 22.15 milliliters. So I'm just going to tell you this because it might not be obvious, maybe not, but these are going to be in excess again. Since those water is in excess, you probably figure since we have it in aqueous solution, the H pluses are going to be in excess. I'm just going to tell you that. It's under acidic conditions. So this is kind of like exactly what we did just now, what you guys did. First thing is to come up with moles of As2O3 from grams, just like you guys did. The next step is to come up with the moles of MnO4 minus from stoichiometry. And then the last step is to take those moles and divide it by the volume. Okay? So going back to 64, I don't have the equation because I was in a hurry. But you're going to go find the equation, and I'm telling you, if you just put the volume, my suggestion is just simply to go get that equation from example 5-6 and put this information underneath it and see where you can get moles. Use stoichiometry to get moles of something else. Okay? that's the best I can do with that now. Okay. So, which maybe if I think about it when I get back to my office, I'll maybe come up with something fancier. I don't know. We'll see. All right. So burning stuff, is that not cool or what? Okay. But you're going to be virtually burning things. Sorry. So part 3 follows part 2. And if you go back in your notes and look at what we did in part 2, we were talking about, actually we talked about taking weight % data and knocking out an empirical formula of a compound. We said, remember the whole 100-gram basis thing? Okay, and then you can take that weight % and turn them into grams. You can use the molar mass of the element to get to moles of that element, etc. So you might want to refresh yourself. This is, actually, I like ending with part 3 because this is bumping up against your unit exam. So you guys need to remember this anyway. Okay, so we can go from weight % data to empirical formula. Remember, empirical formula is the reduced formula. Okay? All right. So when we talk about a combustion of something, basically you are taking a reactant, and on the product side, basically your stuff has oxygen in it. That's in general what combustion is. Okay. So if the stuff that we're burning contains carbon and hydrogen, when we incorporate oxygen in that stuff by burning it, notice that we end up on the product side with carbon dioxide and water. So one of the things I need to emphasize in this sort of problem is, do you see where all of the carbon atoms in the carbon dioxide came from the carbon atoms in that stuff you burned? All of the hydrogen atoms in water came from the hydrogens atoms of the stuff you burned. Okay. Now, I'm going to show you something that looks a little complicated or whatever. We're not going to mathematically come up with x, y, and z variables, or I guess x, y variables, like the 2 equations, 2 unknown things. We're not going to do that. We're going to do it some other way. The other type of problem we need to talk about is not a hydrocarbon, but it's a hydrocarbon that contains oxygen, and you burn it. These are a little bit, I say, harder. So notice that you burn it, you introduce oxygen, and notice you get back carbon dioxide and water. That's cool. The problem is it's a little confounded because your oxygen is not, it's all like, we'll do it and it'll be fine. But notice that you introduce oxygen as another reactant. Not only that, but you have oxygen in your 2 products. So it's a little bit trickier. Here's what I'm saying. If you're burning something that a hydrocarbon with oxygen, you're going to find oxygen last. It's going to be kind of like a mass analysis by difference. So if you were going to do the whole X, Y, Z now, you can kind of see the relationship between the coefficients. Burning 1 mole of this will give you this moles of O2 is what you'd have to add to it, and produce X moles of CO2 and Y over 2 moles of H2O. But this is an algebra class, so. Okay, so like I said before, the cool thing about this is whether you're burning something that is carbon hydrogen or carbon hydrogen and oxygen, all of the carbon ends up as carbon and CO2. It's a wonderful world. Okay. Similarly, regardless of whether you're burning something with only carbon and hydrogen or carbon, hydrogen, and oxygen, all of the hydrogen ends up as those cute little H2 atoms associated with water molecules. Okay. All right. So kind of thought process behind how we're going to work these problems, or how you're going to work these problems. I'm going to show you, it's kind of cool, how it's like, it uses like scrubbers, kind of after you burn something, you kind of scrub the stream, the product stream, and you remove the CO2, and then you have another absorbent that removes the H2O. So it's kind of fun. And the O2 is in excess. It just goes right straight through. Okay, so we're going to measure the mass of the CO2 produced when we burn something. We're going to measure the mass of what we burn, the mass of the CO2, and the mass of the H2O. And we'll be able to knock these problems out. Okay. So we'll have the mass of those two products to knock out carbon from carbon dioxide mass, hydrogen in the thing we burned from the H2O mass. If we have that second type of compound that we're burning that also has oxygen in it, we're going to have to kind of do a little extra on the tail end. Basically, what we're going to have to do is come up with the mass of the carbon and the hydrogen that we know must have been in our product that we burned, and then basically take the product's original mass minus the carbon minus the hydrogen is equal to the oxygen, so just by difference. So let's see. And my video has just, or my sound has just not been cooperating, I guess I should say. Try it one more time. Seems like it should be in the, oh, maybe it's got to be in the headphones. That seems right. Headphone jack instead of the mic jack. That's what I had. Is it trustworthy? Yes. Always a suspect. $1,001, $1,002. Okay, can't wait anymore. See. All right. Oh, see, I got this turned off. Maybe that's my issue. Try again. Because there's this nice lady talking in the back. Or guy talking.
A combustion reaction of a compound with oxygen forms water and carbon dioxide. The water, represented as blue speckles, is trapped in one chamber, and the carbon dioxide, represented by white speckles, is trapped in a separate chamber. The mass gain of each chamber can be used to calculate the empirical formula of the compound.
Is that not adorable or what? One of the things that I hadn't really thought about much till just now, but usually, I don't know about your furnaces, but when I burn something, I've got a residue left. Kind of ash, right? And these problems, basically, it all goes away. And ends up, the hydrogen ends up as in water, and the carbon ends up as carbon dioxide. All right. So this is just kind of a still image of what we just saw. For instance, this is your hydrocarbon. The black is carbon. The white are hydrogens, and that red is oxygen. Of course, it's combining with oxygen. Either they're actually supplying the oxygen to help it burn. You end up with water and carbon dioxide and excess oxygen. So the oxygen just carries on out. This is an excess. Okay, so here's our problem. Now you don't have to, but what I would do is actually kind of consider the general chemistry that's going on. Okay, so if you read this a few times, notice hydrocarbon. It does not say hydrocarbon with oxygen. Okay, so hydrocarbon. So we don't have to worry about the oxygen yet. Okay, and kind of try to emphasize what we're doing here is they give the mass of the sample 0.1888 grams of this. I'm going to put excess O2. Okay, and then when they weighed back the CO2, it was 0.6260 grams. And when they weighed back the water, it was 0.1602 grams. Okay, so that's what we got going on. If you choose to do, yeah. Actually, I kind of like this because the little X and Y, that's going to give us our empirical formula. We're trying to find the X and Y. We're trying to find the empirical formula of this compound. So basically, to let you know what we're going to do, what are we going to do? We are going to take this mass to get to moles of CO2, okay? And then we're going to go from moles of CO2 to moles of carbon. Moles of CO2 to moles of carbon. Do you see for every 1 mole of CO2, we have 1 mole of carbon? Good. All right, that's cool. And then for this one, we are going to go to moles of H2O, okay, and then we're going to go to moles of H. All right, how many moles of H do we have for every mole of H2O? How many people think 2? I do, yeah. So we have 2 moles of H for every 1 mole of H2O. So once we have these moles, honestly, I know it sounds kind of goofy, but really, this is ready for, that's your Y, and this is, in a sense, your X. You have relative moles. Okay, now we need to go ahead and kind of normalize those, make them whole numbers, like we did before. Notice in this, it's kind of strange, but we did not use this number. Isn't that kind of interesting? We do use that number, the mass of the thing you burn, if it has oxygen in it. So we did not use that number. Sorry to tell you. Okay. So do you have any molar masses? Where did we stop? So we're back here. We'll pick on you guys again. So I guess, go ahead if you could knock out the molar mass of CO2 using the periodic table. Thanks. And then we'll have Andrew use this molar mass, CO2, and the mass of the CO2 to get to moles of CO2. So you can't do yours until she finishes. Perfect. I just couldn't resist. All right. Start with that mass. Good. Thanks.
Is that all?
Mm-hmm. And this is mole carbon, right?
Yeah.
Perfect.
I just forgot to put the C.
Yeah. He's going to take it off. He's going to do. So the next, just heads up, guys. We're going to need the molar mass of water, and we're going to use his molar mass of water to convert mass of water that was given to moles of hydrogen. So molar mass of water, periodic table. You get to choose. You guys are getting good at this little tablet thing. Any questions? I'm liking it. I'll let you tap that out too then. You got a calculator. If you write it, I'll just write it here. This is from Andrew. One, 422. Any questions? Perfect. All right, so that's like the little subscript X, right? That's kind of strange. Now we're turning our attention to the water that was produced and going for the hydrogen, moles of hydrogen. So first we need the molar mass of H2O. And these molar masses that have been knocked out, we're going to use these 2 molar masses again in the next problem. Okay, so.
So I'm just gonna take, but I don't know what my top number's gonna be.
Okay, so you're going to start out with the mass of water, the 0.1602 grams H2O
Okay,
over 1.
and then this is gonna be,
Mm-hmm.
but what goes on top?
1 mole H2O.
Oh, okay.
Mm-hmm.
Oh, that's easy.
And but then you're one more term, because that's 1 mole
Oh, the
H2O.
stoichiometry,
Yeah, or the relationship between hydrogen.
where's the,
So it's not stoichiometry, but we said there's 2 moles H for every 1 mole H2O.
sorry, so we need 2 moles,
No, other way around.
2 moles H2 over 1 mole of H2O.
Mm-hmm. And this would be just H.
Okay.
Alrighty. So now you know she's going to look at, you have to go back a few slides, what mass of water was produced. And that's going to be the mass of water over 1, and then the molar mass water to get to moles of H2O. And then to get to that little moles of hydrogen atoms, recognize that for every 1 mole of H2O, you get 2 moles of hydrogen. A really common mistake is to forget that last step. And she's going to give us 4 sig figs.
Oh, that would not be grams. That's wrong.
Oh,
Isn't it, oh, there should be a mole here. Would it be moles of H?
it would be. So for those of us who are wanting algorithms, I think that's the word I want, or how you do problems, this is kind of the cadence or the pace of how you would do a combustion analysis problem to get to the empirical formula. So, all right. So we worked this recognizing that we only had carbon, only had hydrogen. All the carbon ended up as CO2. All the hydrogen ended up as water. Okay. So we're not done yet. We need to go ahead and kind of, I think of it as kind of scaling up those moles. Okay. And so you're going to see on the next slide one way to scale them up. But what I would do, and this might ring a bell from part 2, basically, usually when you're working these problems, you have plenty of time. Unless you're trying to work them like the last hour before they're due. And then it's like time does not work, is not on your side. Okay, so we came up with the number of moles for carbon, was it the 0.0142? 22, thank you. Okay, and then hydrogen 0.01778.
0.0177.
Yes, thank you, 0.01778. Cool, thanks. So now, do you guys remember this, where if you divide both of them by the smallest, things usually kind of fall into place? You don't have to do it this way, but it just helps for me. So, of course, the smallest is that 0.01422. And if you divide that by itself, of course, you get 1 there. And I brought my calculator because I ran out of time in my office. But if you divide 0.01778 by that number?
It's 788.
Thank you. That's what you tried to tell me. 1788. I think we're going to have to multiply by something. So remember we said that this is 1.25. Remember that we said that if you get quarters, which this is, or halvesies, or thirdsies, or two-thirdsies, you can't just round. We can't just say that it's C1, H1, okay? Can't do that. So the fact that it's quarters means quartersies, that I'm going to add a column and I'm going to multiply by 4. That's how I do it. Okay, and of course, 1 times 4 is 4. 1.25 times 4 is 5, right? Okay, so finally we have nice whole numbers to go ahead and say it's C4H5. Does that work? Okay, alternatively, we can kind of just look at the moles that we got, and relatively speaking, with regard to the moles of hydrogen to moles of carbon, we can say, we can divide out what we had and say that we have 1.25 moles of hydrogen for every 1 mole of carbon, and then scale it up from there. Okay, again, recognize we have a quarter-ish going on there. Okay, multiply numerator and denominator by 4. Either way. But it's like all chemistry problems. You just have to say what you're doing and stay organized for your benefit and for the grader's benefit. Any questions? Okay. So let's take a look at the 4 homework at the end, because we're bumping up against, you got the hiccups. That's so cute. We're bumping up against the clock. So I just want to assign the ones that only contain hydrogen and carbon. So if you look at the slide at the end there, the assignment slide, we're going to do a couple of these. So for instance, this one will also be due on Friday. Okay, notice it's giving you a hydrocarbon. It gives you the mass of the carbon dioxide. It gives you the mass of the water. Okay. This one, it's asking for more things than we did. But B, the empirical formula is exactly what we did. Okay, from the empirical formula, actually, and I'll try to kind of throw up some hints in case you find it helpful for you to get at home. But the part A is this A question is what we talked about in part 2. And actually also C was also in part 2. So 43 will be due, and I'll put hints up because I know everybody's anxious to go. Okay, and actually this one, don't do 44 because we're going to do an example of this on Friday. That might be the only one you can do. What? Yep, only do that one. Okay? And I'll throw up hints. Any questions? So we do have a session in the conference room right now if anybody's interested. We can take a break or so, 3-ish or so. Take 5.